Hello everyone and welcome back to my channel Gyan Sampada. Today we are going to continue with another topic related to ferromagnetism after studying the quantization of spin waves. So the concept of today's class is the thermal excitation of magnons and its corresponding density of states. So we know that magnons can be just created by thermal agitation or the thermal excitation. So at absolute zero, as such, there is no magnon, or we say in the ground state of ferromagnetic material, magnon number is equals to 0. But when the temperature is varying or with respect to the field or the perturbation, we can observe the creation of magnons, and today we are going to derive the equation for the density of states, which is nothing but the total number of magnons which are excited in all the states of the spin system. According to our previous knowledge, we know that each magnon lowers the Z component of total spin by 1 unit, that is due to the thermal excitation. And generally that 1 unit will be with respect to H cross, which we have discussed while discussing about spin waves and the magnons. We noted that the total spin is going to reduce by 1 unit of H cross, whereas the magnetization will vary by gamma H cross. Thus, when we consider thermal excitation, we can say the total number of magnons in all the states which are excited in the spin system at any given temperature T can be given as summation Nk over K, where K is the wave vector, equals to the integration runs from 0 to infinity, which implies for all the states of the spin system in a frequency range of d omega into z of omega into nk bar, where z of omega is nothing but the density of states, that is number of states k per unit frequency range d omega, and nk bar is the average number of magnons in a given state specified by k, that is the wave vector. So this is a standard equation to find out the number of magnons. And if we consider a three-dimensional space, the number of modes of the wave vector which are less than k per unit volume will be equal to 1 by 2 pi whole cube into 4 pi k cube divided by 3. So here we can observe it is similar to that of a volume of a sphere, that is 4 by 3 pi r cube. Instead of r we are having k or k by 2 pi, that is corresponding to the reciprocal space. So that's why we can represent the number of modes equals to this term. So what we are going to try is that we need to find out the total number of magnons, which is nothing but the density of states. And for that we are having this formula. So d omega is the range of frequency or a short interval of frequency, and z of omega is the density of states, whereas nk bar is the average number of magnons. So if we substitute the values of z of omega and nk bar and integrate over a range, then we can get the density of states. So now we are just finding out what is the value of z of omega and nk bar, and based on this we can say that the number of magnons z of omega with frequency d omega can be written as z of omega into d omega, which will be equal to differentiation of this term, that is 1 by 2 pi whole cube will remain as it is, 4 pi by 3 is a constant, and differentiation of k cube is nothing but 3k square into dk. So this equation we have differentiated so that we can find out what is the number of magnons in the given frequency range d omega. So when we simplify it, we can observe 3 is going to cancel out, leading to the equation number 2, which is z of omega is equals to 1 by 2 pi whole cube 4 pi k square as it is dk divided by d omega. Let us call it as equation number 2. Here we can observe that the wave vector k is also variable, and omega is also variable. And here in equation number 1, integration is with respect to only variable omega. So we need to convert all the terms whichever are there with respect to k into the same system, that is omega. And for that we need to consider our previous knowledge of dispersion relation, which is nothing but h cross omega is equals to 2j dash sa square into k square. That is, we are considering longer wavelength limit only, where we have omega directly proportional to square of the wave vector. So in detail derivation is given in our previous classes. So you can just go through it and understand how to derive this dispersion relation. So as I told you, in equation number 2, we need to replace k in terms of omega. So here differentiating this equation again, we get h cross d omega is equals to 2j dash sa square as it is. K square differentiation is 2k into dk. So when we rearrange, we will get dk by d omega equal to h cross divided by 2j dash sa square multiplied by 2, that is differentiation of k square is 2k into dk. So that will be 4j dash sa square into k. But still here also we are having a term of wave vector, and in order to remove this term we are again going to use equation number 3, which is the dispersion relation. And when we substitute the value of k, which is nothing but k square is equals to h cross omega divided by 2j dash sa square. So k will be equal to square root of h cross omega divided by 2j dash sa square. So as it is in the denominator, we have just reversed it and written like this. So clearly we can observe some of the terms are going to get cancelled out. So finally we are remaining with dk by d omega is equals to 1 by 2 into h cross by 2j dash sa square raised to half into omega raised to minus half. So when you are cancelling out the terms, be careful because here the power is 1 and here power is half. So here I have written 4 as 2 into 2. 2 has been written as it is and another 2 is going to get cancelled out. So we are remaining with only root of 2j dash sa square in the denominator. And only term which is not going to cancel out is omega. So it is 1 by root of omega, which is nothing but omega raised to minus half, and we are calling it as equation number 4. Now we need to substitute this value of dk by d omega in our equation number 2, which is about the number of magnons in the frequency range z of omega into d omega. So when we substitute the value, we get z of omega is equals to 1 by 2 pi whole cube into 4 pi k square dk by d omega. Instead of dk by d omega, we need to substitute this value. 4 pi is going to get cancelled and we are remaining with 1 by 4 pi square into h cross by 2j dash sa square raised to 3 by 2 into omega raised to half. So simplification is very easy. Just we need to substitute this value and we need to cancel the terms which are coming in the numerator and denominator. So let us call this as equation number 5. So the term z of omega is ready and this is only depending on omega and other things are constant. So this can be substituted directly in our equation number 1. And this equation number 5 gives the number of Magnon modes per unit frequency range, that is the density of modes of Magnons. So this is very important expression when we consider the Magnon concept. So with respect to frequency, how density of states is going to change. So according to this equation, if we need to increase or decrease the number of Magnon modes, then just we need to do is that we will have to vary the frequency. So next, in order to find out what is the value of nk bar so that we can substitute it back in our equation number 1, we are going to consider the thermal equilibrium condition, because at thermal equilibrium the average value of Nk will be given according to the Planck's distribution function, according to which Nk bar can be written as 1 by exponential of h cross omega divided by kBt minus 1. So this is another notation to represent the average number of magnons. So let it be equation number 6, and now the final step is to substitute equation number 6, that is Nk bar, equation number 5, that is Z of omega, in equation number 1, which gives us the total number of magnons excited. So summation Nk over all the possible wave vector values will be equal to integration from 0 to infinity. This is Z of omega value, and this is Nk bar value in the range d omega. So next we will just simplify. The constant terms which are not depending on omega are taken outside the integration mark, and only the terms with omega are kept within the integration sign. And we are noting it down as equation number 7 because we know this is the type of integration which cannot be solved directly. So we need to take use of substitution method. So put x is equals to this exponential term, that is h cross omega divided by kBt. Thus omega will be equal to kBt x divided by h cross, which can be substituted in the place of omega, and thus d omega will be equal to kBt by h cross into dx. So this value can be put in place of d omega, and h cross omega by kBt is nothing but x. So when we substitute it and solve for summation Nk, we get the integration from 0 to infinity of root x divided by e raised to x minus 1 with a number of constants. So constants are as it is, and the value of the integral is equals to 4 pi square into 0.0587. So if you substitute the value of this integral, we can say that summation Nk is equals to 0.0587 into kBt divided by 2j dash sa square raised to 3 by 2, because this is the integral which will have this value multiplied by 4 pi square. So 4 pi square is going to cancel out, which will give us this final equation of summation Nk over the possible values of the wave vector. And this is the expression which gives the number of magnons excited thermally per unit volume. So clearly we can observe the number of magnons which are going to get excited are directly proportional to T raised to 3 by 2. That is the temperature term, because all other things are constants. Thus we can say if you change the temperature, we can change the number of magnons present in the spin system. So this is the details about today's class, where we discussed about the density of states of magnons based on the thermal excitation of magnons. So each step is explained. Intermediate simplifications are very easy. So I hope you can do it, and in our next class, based on this expression itself, we are going to solve for Bloch T raised to 3 by 2 law, which is again a very significant topic when we study ferromagnetism. So this is for today's class. See you in our next class. Till then, stay tuned, study hard, and thank you for watching.